Welcome back to another Explainer, everyone. Today we are tackling a massive, honestly pivotal shift in the world of robotics. We're talking about leaving behind those brittle frameworks of the past and stepping fully into the complex, beautiful world of modern kinematics. Specifically, we're zeroing in on its geometric foundations. Look, if you've ever dealt with a highly expensive robotic arm that suddenly just freezes up or glitches out mathematically right when you need it most, well, you are in the exact right place. We're going to demystify exactly why that happens, and more importantly, how to fix it.
Okay, let's dive right into this roadmap. First, we'll cover when traditional methods fail, then the geometric robotics solution. Next, we'll hit twists, wrenches, and exponentials, followed by the mathematical trade-off, and wrap up with real-world applications.
Section 1. When traditional methods fail.
To really establish the stakes of this engineering problem, let's look at a classic scenario that absolutely haunts engineers. Why does the traditional Dennevit-Hartenberg, or DH method, completely fail when an arm reaches straight up? It's a notoriously frustrating issue. The physical arm is perfectly fine, the motors are humming along perfectly, yet the mathematical model telling the robot what to do completely flatlines.
Let's take a breather and put an exact name to this robotic freakout. It's called a coordinate singularity. By definition, it's a mathematical failure point where the traditional DH parameterization basically loses a degree of freedom. The math literally divides by zero or just collapses on itself. So it becomes entirely impossible for the software to calculate the next movement, even though the robot's physical hardware has plenty of open air to move into.
And if we plot a robot's workspace reach limits out on a graph, it perfectly visualizes exactly where these older methods collapse. These reach limits represent the physical volumetric boundaries of the arm's potential motion. But under the traditional DH method, hitting certain orientations near these boundaries creates a massive mathematical roadblock. The model simply cannot handle those extreme alignments. Which leads us straight to Section 2, the geometric robotics solution.
Now, what's really interesting about this is how we actually fix the problem. If DH parameters are causing our models to freeze up, what's the replacement? Enter Lie groups and Lie algebras. These are advanced mathematical frameworks originally developed for continuous transformations. By applying Lie group theory directly to 3D rotations, we completely bypass those traditional coordinate singularities. The math remains continuously robust no matter how that robotic arm twists, folds, or stretches out.
Specifically, we rely heavily on the special orthogonal group, or SO3. Now, I know, special orthogonal group sounds incredibly intimidating, but stick with me here. It's simply the specific Lie group that encompasses all rotations about the origin in a 3D Euclidean space. You can basically think of it as a specialized, ultra-reliable tool for handling complex multi-body dynamics without ever triggering the glitches we used to deal with. But I do have to throw in a quick warning for anyone who has ever studied robotics. There is a classic, agonizing pitfall here. When working with SO3, you must always, and I mean always, remember that your rotation matrices need a determinant of exactly +1. If you crunch the numbers and wind up with a determinant of -1, well, you haven't just rotated your robot. Mathematically, you've accidentally mirrored your robot inside out into another dimension. Yeah, your simulation is definitely going to let you know you've messed up there.
Moving right along to Section 3, twists, wrenches, and exponentials.
We are now officially opening up the modern kinematics toolkit. In geometric robotics, we toss out standard clunky vectors and replace them with twists and wrenches. Let's rapidly break these dense terms down. Twists represent velocities in space, so both linear and angular, wrapped up into one cohesive, six-dimensional package. Wrenches, on the other hand, represent the forces and torques applied to the system. Understanding these two foundational concepts is absolutely crucial, because they're the primary mathematical forces driving our modern manipulator modeling.
And tying those twists and wrenches together is the product of exponentials, or PoE formula. Think of PoE as the ultimate mathematical savior for rigid body transformations. It gives us this beautifully unified framework for calculating everything in SE3, that's the special Euclidean group, handling both rotation and translation at the exact same time.
Let's move to a practical scenario and see how this builds logically. Step 1 is defining a screw axis for, say, a 2 degrees of freedom joint. A screw axis just describes the exact line in 3D space that the joint rotates around and translates along. Then, step 2 is calculating the forward kinematics using that PoE formula we just talked about. By systematically multiplying the matrix exponentials of those screw axes, you effortlessly find exactly where the very tip of the robot arm is sitting in 3D space.
To firmly ground this in reality, let's highlight a quote from the definitive text on the subject. As noted here, Lynch and Park's geometric framework simplifies complex multi-body dynamics. By fully adopting this modern robotics approach, engineers can design incredibly complex, highly articulated machines entirely without getting bogged down by the fragile, error-prone equations of the past.
All right, Section 4, the mathematical trade-off.
And this brilliantly illustrates the big debate in modern kinematics today. On one side, you have the Dennevit-Hartenberg parametrization. It's what almost every engineer learned for decades, but as we know, it's fundamentally prone to those coordinate singularities. On the other side, the product of exponentials framework. PoE offers mathematical perfection, which is absolutely vital when designing something as complex as a modern 7-axis collaborative arm. The trade-off? Well, PoE comes with a significantly steeper learning curve. You really have to be willing to master Lie groups and matrix exponentials.
Finally, Section 5, Real-World Applications. So who actually uses this math? Let's bring this abstract geometry firmly down to earth. If you're wondering what the practical so what is here, just look at the professionals relying on these tools every single day. Industrial integrators absolutely need modern kinematics so their highly expensive manufacturing robots don't crash when reaching an awkward angle. Interestingly enough, CG animators heavily rely on these exact same principles so their digital character rigs move naturally rather than twisting into terrifying broken shapes on screen. And of course, engineers building advanced 7-axis collaborative arms depend on it completely to ensure safe human-robot interaction.
So the crucial point is this: mastering advanced manipulator modeling isn't just some academic exercise. It means consciously choosing mathematical elegance to solve very real, very costly physical failures. Upgrading your toolkit from DH to PoE is practically mandatory for modern professionals who want to build and program robust, glitch-free robotic systems.
For those of you ready to deepen your expertise, here's how you can continue the journey. Channel that focused learning energy into reviewing Jacobian singularities to see exactly where velocity algorithms break down. Try a practice quiz on the properties of SO3 to test your grasp on rotation matrices. And I highly recommend diving into further reading with Lynch and Park's definitive book, Modern Robotics: Mechanics, Planning, and Control.
I want to leave you with a final thought as you look over these geometric foundations. We've seen how remarkably reliable and powerful these advanced models are, effectively curing the mechanical headaches of the past. But they undeniably demand a deep understanding of complex, abstract math. So ask yourself, is mathematical perfection really worth the steepest learning curves? I'd argue yes, the summit is absolutely worth the climb. Conquering this math unlocks the future of robotics. Keep learning, keep exploring, and I'll catch you in the next explainer.